Hello and welcome everyone to a blend of analysis, one product, every discipline. My name is Robert Warren. I'm a simulation specialist here at GoEngineer, and I'm located in Cleveland, Ohio. Today we're going to talk about a product development, and that product that we're going to be looking at is the GoBlend blender. This kitchen appliance boasts of being fully designed in SOLIDWORKS and 3D Experience. This blender has been scientifically optimized for its structural integrity, electronic thermal management, manufacturability, and of course its capability to blend a killer smoothie. Touchscreen controls and a smart Wi-Fi connection round out its expected capabilities. Let's take a look at how this blender went from concept to optimal design. Before we begin, one additional requirement: marketing wants the blender base to represent the company logo. So where we're going to go in this presentation is just talk about the concept, how we got to the model that we're going to be looking at. We'll talk about structural analysis, fluid analysis, manufacturability, and electromagnetics. So let's talk about the blender, the 3D model, and the journey of how we developed this design so far. So we did a lot of research, right? This is where anybody would start. We wanted to understand, what others are doing, what's on the market now. So we investigated. We wanted to understand all the components necessary to create the product. We put pencil to paper, literally. We drew out the design, the different ideas that we had, and we took those sketches and we turned those sketches into a solid model. Now, along the way, there were some pitfalls, right? Manufacturability, for one. I talked to our plastics engineer, Bill Roos. He indicated, hey, we can't injection mold this. That corner is pretty much impossible. So, did a lot of redrafts just with the initial thought process of the solid model. During the design process, we used structural analysis, computational fluid dynamics, manufacturing analysis, and electromagnetics to help develop the blender to what we see here. Let's look at the picture handle. The handle looks stylish, and our intuition indicates it can withstand a large load, but we do not want to move up to a prototype before we confirm the handle can withstand 25 pounds of product in the picture. It's way more than what we would normally expect. We know we need to stay below a stress of 1200 psi to keep a factor safety of 2 or better. Let's see how the handle performs. Inside of SOLIDWORKS, we can save the model to 3D Experience platform. On the right-hand side of the screen, we have a direct access to save the model to the platform, even choosing specific bookmark to place the model. Once the model is uploaded, we can select the model from the bookmark and launch our structural analysis tool. First step to setting up the model is to use the finite element representation, a FEMREP. We're using an automated FEMREP to generate the solid sections and initial mesh. Choosing the solid sections tells the software what parts we want to use in the analysis. Renaming the solid section is a good rule of thumb, and we can specify the material to use right in this property manager. So we can see we're choosing a plastic. It's going to be a polycarbonate, and we can see the simulation data associated with that component. We're going to do the same thing for the next solid section. We're going to rename it. That name is handle, and we're going to pick a material, and in this case is going to be a nylon 610, and we can see the material properties associated with it as well. The mesh was created during the auto FEMREP stage, but we want to refine the mesh further. We can edit the mesh for both solid sections. So by editing these, we can go in and we can refine the mesh size. We can also tell it no sag, which means it's going to map the geometry perfectly. And we can see that refinement on the handle itself. From here, we're going to add some connections, and in this case, we're going to add a tie. Now, in reality, this handle is a kind of a press fit or a friction fit. However, to best mimic what's happening in the model, we're really pushing down, so it's going to always be in contact. We're just going to use a tie between these two components, basically bonding or holding them together inelastically. We're going to go ahead and save the study. From there, we're going to start our static scenario app. We can see we're going to name the simulation. So we'll give it a name here. So picture handle. And we chose the finite element analysis model that we just created previously. We're also going to go in and add a procedure. So we're going to add a static step. And we're going to choose our boundary conditions. So we will assign a clamp to the upper portion of the handle, basically saying, okay, this is where it's going to be held, maybe with our thumb and our forefinger. We're also going to add a roller slider to the back face of the handle. This is where it would be maybe in contact with the palm and the other fingers in our hand. So we're going to allow it to kind of move right and left there. We're going to assign our force to the bottom face. And again, this is going to be 25 pounds, probably a lot more than this pitcher would ever see in real life with regards to a smoothie. From there, we're going to go ahead and solve the analysis. So we can bring up the solve property window, and we have a lot of different options. We can solve locally. We can also solve on the cloud. We're going to do a local interaction here. With this specific version of the software, we get 4 cores embedded for free, and we'll go ahead and start that solve. Once the solve is complete, we can take a look at the results. Now we can see stress on the handle. This is the first result, and you notice that we have 1 increment. That's because this was a static study. So we're looking at the end result. And we can see our stress, the maximum stress is 885 psi. Remember, we had to stay within 1200 psi. So we're looking pretty good with respect to those results. We can actually animate this. Notice that this is exaggerated. The pitcher is not deflecting this much, but it gives us a feel for how the pitcher is going to deform, how it's going to move. And we're seeing that holding that handle, right, we're expecting that deflection in the direction that we have there. So that makes sense to me with respect to the results. We can go ahead and change the deformation scale as well. So we can edit that plot, and we can shake this back to a deformation scale of 1, basically a 1-to-1. So this is a true deformation in the model. We can also look at different things within this plot. So anywhere I move my cursor, we have a probe tool, so we can give us the value of stress in those areas. The other thing with respect to this is we can look at the displacement. So the displacement allows us to kind of understand how much is this moving, and really 0.4 millimeters, so half a millimeter at that maximum distance, really isn't a lot. We can also go in and do plot sectioning. So we can pick different planes to section through, and with that we can actually even change to the stress plot with the section still on and understand, what is the stress on the back of the handle. Maybe we'll move this section a little bit to understand what is the stress right through that fillet. So if I pick on my plot sectioning again, we can move that section and we can understand how far the stress penetrates through the arm itself. So a lot of good feedback with respect to the outputs. From there, what I want to do is go back into 3D Experience, and I want to make sure that I have all of my components associated in that bookmark that we talked about earlier. So I'm going to pick up the relations of this model, and I'm going to pick up the results in the finite element model, drag those into the window, and we now have access to those results again. when we go back to the picture linear for the GoBlend structural in that bookmark, we can always get back to our study very quickly. So with regards to structural, I did a couple more analyses. One was a drop test, and I used SOLIDWORKS Simulation Professional to perform this. Now the drop test is on the picture itself and the blade assembly. We did not include the handle on this one. So moving back into SOLIDWORKS Simulation, I'm going to go ahead and start a new study, and I'm going to choose drop test. Now this is a nonlinear caveat of the Simulation Professional module. I have stainless steel assigned to the blade and the shaft for the blade, and then we have the polycarbonate assigned for the picture itself. We have a fairly refined mesh on the model, so not too coarse but not too fine, so it looks pretty good. And we're going to look at the setup. So I picked the right plane as my direction of gravity. I also told the software that it's going to be 36 inches above the ground, so we're giving it a drop height. However, we could give it a velocity at impact as well. And I'm specifying that the target is rigid, however, it could be flexible, could have some give to it. And then I'm also going to tell the software how many seconds, microseconds, past impact we want to see the results. Now the next step is really to run the study and then take a look at those results. So I already ran the study. Let's go ahead and jump into the results. So here we can see, we can animate the results. We can see it kind of come in contact with that ground plane. We can see the stress developing as it comes into contact. I'm going to go ahead and edit this, and I'm going to make it an automatic scale. So this is exaggerated again, but it's really showing how that deformation would be occurring on an exaggerated scale. So we can actually see almost a buckling on that lid or on the edge where the lid would connect. We can look at displacement, we can look at strain, we can also look at the response. So there we saw the response graph of the force of this impacting. Now, again, this is a nonlinear caveat. It is limited, right? We can't include the fluid that's associated with being inside the picture. We do not have the lid, we do not have the handle just because of some contact considerations. We'll see later in another structural analysis we can include those. So another structural analysis was the press of the lid onto the picture itself. Now we have the gasket seal, and I originally put 5 seals on this gasket. However, in talking with Matt Schreck, another engineer here, he said, there's usually only 2. So he actually modified the model, removed 3 of those seals on that. Now we know we need to press this lid on, and we want to keep the press force under 30 newtons, or roughly 6 pounds. Anything more than that would probably be too much for most people to press this on, or it would just be a bad experience. So what I did was I loaded this model into 3D Experience, and then I shared this with Matt Schreck. So Matt is a lot better versed in the nonlinear caveat of the software than I am. So I just simply shared this with him, sent him a message saying, hey Matt, can you take a look at this model? And I did all of that through 3D Experience. He went ahead, downloaded the model, and what that did then was he was able to set this up. So we're now looking at Matt's screen. So you can see he modified the model to have only 2 seals on that gasket. And he went in and he is going to modify the assembly a little bit. Now, he also cut off the bottom of it. We don't need to access the entire picture, just mainly the upper lid. We want to understand the press of the gasket. He's also starting a FEMREP here, and he's doing this as an axisymmetric. So why analyze the entire model when really that gasket is symmetric 360 degrees? So he's going ahead and he's also assigning a mesh size when this FEMREP generates. So when he selects OK, we can see that that is now cut along that section with the axis, and this is an axisymmetric model. So he's going to go ahead and add in the materials, so the polycarbonate for the lid and the pitcher, and he used a hyperelastic silicone for the gasket itself, or hyperelastic rubber. We now have that model set up as far as the finite element representation. He's now adding a tie between the gasket and the lid. This is an overmolding process, so we're assuming that those two are bonded or tied together. He's now going to go in and start setting up the model. Now, different from what I did previously, this is an explicit dynamic analysis, meaning we're going to actually iterate the movement of this through time. We're also going to understand what is happening along that entire application. He also said that he's taking the top of this lid and he's going to move it vertically 15.25 millimeters. That's the distance to kind of push this down. He's solving this on the cloud, and he's using 8 cores. 8 cores are available through the cloud for free for that solve. And once that solves, we can take a look at those results. And with these results, we can actually step through time. You can see that on the upper right-hand corner of the screen and understand what is happening as this solves. So we're looking at von Mises stress, and we're looking at this as how it is kind of moving down. Now he's going to change the results here a little bit, kind of see a cross section of this. Because it is axisymmetric, we can look at this in a full 360 degrees. He's animating the result, and we can see how the stress develops in the rubber or the silicone seal, and as it's kind of being pressed down along as it drags along that pitcher wall. We can also look at things like contact pressure. Now, one of the things that we're going to see with this is the contact pressure is actually fairly low. That's not what we wanted. We wanted a pretty high contact pressure to hold this in place. We are noting that the lower seal has a higher contact pressure than the upper seal. What we may want to do to kind of even that out is maybe shorten that lower seal a little bit. So that's kind of adding to the contact pressure there, but there's very little contact pressure on the upper one because we're already making a lot of contact with the lower seal, because that pitcher does have a sloped wall. The other thing that we're going to look at here is we're going to get an XY plot, and we're going to look at the force to push this down. Now, unfortunately, the force is a little high. It's 180 newtons, roughly 40 pounds to push this down. So our contact pressure isn't as high as we want it to be, but our force is. And that's probably because of that lower gasket lip being too long and the pitcher kind of angling down. So we need to do a little work on this model to really get that lid straightened out. So we have to revisit the seal design, but we're able to see that up front before we go to prototype this. So this is invaluable information to save us money on cutting that mold. We are able to see that virtually. So let's look at an advanced drop test. So this kind of validated a little bit of that lid issue as well, in how it would be kind of held on. So what we're going to do is we're going to drop the entire pitcher. The handle with that friction fit, we're going to have the lid already pressed on with an interference fit. We have a fluid inside the pitcher itself, and we're going to drop it from a certain height and kind of understand what's going to happen. So Matt did this as well. He said, you know what, let's look at that lid further and see, is it going to hold on as we set up this explicit dynamic analysis to drop this pitcher down. So you can see he's adding the meshes into the model. Pretty refined mesh on the handle, the basket handle itself, on the lid, and on the seal. The pitcher is going to be fairly coarse, not as refined as the rest, but we're going to get a mesh on that here as well. And then he also added a ground object below as well. So we can see he's kind of setting these up. He's going to go through and manipulate the overall mesh size. He's actually doing a hex dominant mesh, something that's very specific to 3D Experience and Abacus, which is actually pretty nice. Now, from there, he generated the mesh. We're going to go ahead and look at adding the materials into the model. So again, he's going to add these into the solid section, so the appropriate polycarbonate for the pitcher, the appropriate polycarbonate for the lid, the silicone for the gasket, and the nylon for the handle itself. So he's adding those all into the model. So we have those materials assigned. From there, we're going to go ahead and set up the boundary conditions. So inside of 3D Experience, what we can see is going to switch over to Structural Mechanics Engineer, and he's going to start adding in things like the initial velocity. He added in the general contact into the model, and this is actually pretty interesting what he's doing here. He's adding something called spherical particle hydrodynamics. So this is called an SPH element. So he's able to take those bodies that represent the fluid inside the pitcher and add to them a way of finite element analysis, treating them as though they are a liquid. So the very cool part about that is when we drop this, we're giving it an initial velocity down. Those particles inside the pitcher are going to behave as though they're a liquid, and it's going to add additional force, additional impact into the design. Now he's running this on the cloud. He's using credits. Credits are consumable, and he's running this with 192 cores of cloud computing power. And we can take a look at the results after that finished running. So we can see here we're back on my screen. So Matt ran the results. He felt that they looked pretty good. He messaged me through 3D Experience and said, hey, Robert, please take a look at the results. Tell me what you think. So what I'm doing is I'm actually pulling those results down from the cloud. So we're accessing those, and I can start looking through them. So we can see when I fast forward to the very end, what a crazy result this actually is. You saw the fluid kind of coming out of the pitcher. You saw the lid fly off, so we don't have enough contact pressures, validating that from this impact result. We can also see the basket flying off of the pitcher as well. We would expect to see that. It's only a friction fit, of gravity effectively. And we see the particles. We can see the fluid leaving the pitcher, which is the really cool part of this analysis. So this is a finite element analysis using an SPH element to represent the fluid, which is really, really cool. So we can see this animation. We can see what that would look like. I am prone to dropping things. This would be all over my kitchen cabinets if we stick with this design. We need to find some way of holding that lid onto the model. Now we can see more than just, hey, we're going to spill the liquid. We can look at things like stress on the pitcher. How does this compare to the maximum stress that the polycarbonate would be able to see, right? Are we going to be cracking the polycarbonate during this drop? What is the stress on the basket itself? Is that within what the nylon can withstand? Kind of understand what the pitcher looks like. The lid itself, we probably would want to expand the ground plane so that the lid would be in contact with it as well. But, first pass on a drop test, but we're kind of getting a good feel for what this would look like. So we can see displacement here being shown as well. So a lot of good value with that drop test. So structurally, we're looking pretty good with respect to the model. We still have to do some rework on the lid itself, but overall, we're looking pretty good structurally.